I will firstly give a quick introduction, who we are, what we do, and how we do it. And then I want to kind of introduce this high-fidelity modeling. Of course, it's a buzzword. I want to briefly talk about what we're doing with it and how do we understand this modeling approach, which is not actually an approach, which is an approach of large meshes. And I brought with me 3 examples on where we apply these kind of high-fidelity models. The first one is a very short one. It relates to soft body impact, the topic of today, to bring together these worlds of aerospace and automotive. So it suits quite well. It's how we compute or how we calculate composite crash absorbers. And the last example, I will go a little bit more in detail on this one, is how we use these large models, these very high fidelity models, to streamline it into a structural simulation coupled with an FSI simulation, which is not done in our house, but we prepare the models and the results, which are then, let's say, connected to the FSI simulations. We are the Institute of Lightweight Engineering Polymer Technology at the TU Dresden. We do obviously with lightweight materials, but and we there cover the whole chain of coming from the material over the manufacturing process, in the design process, testing, and obviously modeling of these. And there are a couple of key figures. This is such a nice slide. We have maybe some important figures are here. We are quite a large institute. We are around about 255 people, 250 people, more or less. Of course, not fully full-time equivalents, but associated with us, working with us. So it's one of the larger, or one of the largest institutes at TU Dresden. And how we, obviously this means we need to do, or we are doing a lot of projects. And this is the second figure I want to raise your attention to. So how do we do projects? So roughly 1/3 of our projects are strictly basic research projects. The projects which are in Germany funded by the DFG, where no industry is involved, which we do basic research, which is fully published, fully available to the public, and we do push scientific borders. And the second chunk is the so-called application-oriented, application-near projects. These are the projects we have already heard about, which are where industry and academia gather to cover or to capture, to tackle a problem, innovation project, innovation aim, in order to push innovation in Germany, sustain work, labor in Germany, and ask, therefore, the government whether it's worth to give money to do this together in order to push the industry, the engineering in Germany. And the last chunk of work is a strictly direct related work with industry. This is work which is mainly not available to public. We are often not allowed to publish this, so it's direct related work. It's always confidential work, which is typically on more shorter time scales. One slide of what I already have been talking about is what we're doing. So we cover, let's say, the whole design and structure chain with regards to lightweight applications, lightweight structures. So we start at a very small scale, at the material level, where we design the material, but we also test the material. This is a very important part. We test it on a small scale, on a material testing level, up to a structural level. So we will see some examples of tests we perform. The tests I brought with me I show are more on the high velocity side, but we do structural testing as well. We go through the design process where we take into account boundary conditions, the structured designing process, how to incorporate the composite material, which makes life a little bit harder, since the composite material, the material somehow evolved through the designing process. You need to take into account also constraints from manufacturing, constraints from your design allowances and so on. So it's a very iterative process And this is, of course, then accompanied by, almost always accompanied by simulation. Here as well, we cover manufacturing simulation, but structure simulation as well. We have one of our major parts is processing, so composite processing, composite manufacturing. This is work we do quite a lot, and of course the quality assurance and LCA is a large part of our work as well. So in total, the uniqueness of our institute is probably that we cover the whole chain here, and through also different scale levels. And one word or one slide to our group. The group of computational methods and together with my colleague Bernd Grüber, we're around about 15 people in this group, mainly related to simulation and modeling work, not only, but basically or mainly related to that. Of course, modeling and simulation is done in the other working groups as well. So when it comes especially to approaches, which I would say are, let's say, standard or state of the art, then we use them right away. What we mainly do is we look at novel, let's say, problems, issues, novel software, how to combine the software, how to get it into the designing process and the manufacturing process integrated. So, and also to look at structures and systems. So this is a challenge which we are facing. How do we actually get the whole systems, let's say, modeled and virtually represented in order to elaborate what's actually the effect of maybe a small scale change environments of how to use softwares, simulation software, physically based software to be integrated, to be connected, which data need to be exchanged between reality. So, for example, when we talk about IoT devices and manufacturing, how do we link these devices and get the data and do elaborate analysis with this data. But of course, coming from a couple of years ago, one of our major work still is composite modeling, failure modeling, damage modeling, and these material modeling related work. Okay, and one important aspect, the last aspect I want to raise here regarding, let's say, our institute, the RLK, is that we are a Rolls-Royce, so-called University Technology Centers, UTC Dresden. We are the UTC for lightweight structures and materials and robust design. So the UTCs, so Rolls-Royce has a network of UTCs of all over the world, which serve, let's say, as a technology hub or innovation hub specialist for certain topics. So as you see, we are the specialists here for lightweight structures and materials, where Rolls-Royce may refer to if they have a problem and how to solve it and how to approach this problem. So all over the world, I think it's round about, or it says here, 31 UTCs, where we have a nice networking event, and in this way we also have quite an international impact, or this network has a large impact, especially on our international relations, international academic relations. Also, the UTC, the last thing for this slide, the UTC is not only the RLK, which is the biggest part of the UTC, but it also has partners from TU Dresden here, for example, the Institute of Turbomachinery and Fluid Dynamics, who also contributed to a part of the work which I will be presenting later on. Okay, now talking about high-fidelity modeling, as I already said, it's more or less a buzzword. It sounds nice, but what does it actually mean? We use high fidelity in terms of, let's say, big or let's say models which are very finely resoluted, which are have a very high mesh density. So, and you may say, so why do we need it now? We didn't need it before. Well, actually, we needed it before, but we couldn't do it. We will see that we are with a very high resolution now in the position to actually capture very localized phenomena, especially in the field of failure modeling. and as we will see such an example for the crash tubes. And the next reason for using high-fidelity modeling is especially for composite very relevant to capture the material adequately. So in composites, as many of you know, you have these typically this ply-wise setup, which leads to a very fine material resolution if you want to model it explicitly. But this is actually needed because the governing failure mechanisms actually happen in between the plies. So we need this very localized failure initiation modeling because it implies a lot of results for the structural behavior. And of course, we are now able to really capture geometric details. So these details might be little tips, for example, in an engine, which then decide whether the efficiency of an engine is larger or smaller. So we might cover small gaps between screws and things like that, or in terms of contact modeling. So this enables us to capture more geometric details. And the last reason is a rather blunt statement here, because we can. So actually, we are now in the position to really use larger hardware resources. They first of all get available, and second of all, so that we can use it, and with the development of HPC computing, they are actually there to use. So, in this mixture, we always looked at higher fidelity models, and now we would say these models I show you really deserve the label high fidelity, and we're now in the position really to cope with them. And I will give 3 examples how we do that. The first one is a quick example regarding the so-called soft body impact. So as I said, at our institute, we do a lot of testing. The soft body impact is an impact scenario which is largely or typically used in aerospace engineering to capture the bird impacts in the design process and to design the engine according to these impact scenario. And with this soft body, you kind of emulate this structure of a bird and use it in the preliminary design phase. So there are several ways of applying such loads. We use here 2 ways, in a kind of a linear way and with a gas gun, and also in a spin rig. We apply soft bodies. It's called, it's often gelatine, or we use gelatine for that. And here you see this linear impact where we basically shoot a gelatin block on, in this case, a generic fan blade. And in this case, actually, the energy is brought in by the impactor, by the gelatin block. So a slightly different or completely different load case, although it looks the same, is the other one, the next one next to it, this load case. So in this case, actually, the blade is rotating here at almost 8,000 rounds per minute, and the gelatin is released and exactly hits in a very complicated time manner. At 3/3, it hits, as you see here, it hits exactly the blade where it should hit. So this is a more, let's say, application loading case. However, it's more complicated. That's why we use this multiple step impact load case. Okay, and why I'm referring to this testing, we are obviously here to talk about modeling. Of course, first of all, modeling always needs the physical relation. You need to have the phenomenon you actually want to model. It goes very, very hand in hand. This is also why in our working group, everybody or each participant has some modeling experimental work as well, because this is something which always goes hand in hand. So you need to know what's happening, what you want to model in order to model it, or to simulate it. And I want to just briefly give here this example. This has also been performed together with DYNAmore, with André Hauve, within the project Extreme, Horizon 2020 project. It was where we took on exactly this challenge of modeling, of simulating the impact behavior of this generic fan blade. And as you have seen the videos, it looks rather, let's say, simple, but if you look closely, it's a very complicated material structure here. Just exemplarily, you have the you see the geometry of the single plies is complexly stacked. You have the root section, which has its own representation or its own stacking sequence. And what we did here, we used quite a high resolution to model each ply separately to capture the failure behavior. And this refers to the high fidelity aspect of capturing the material, the actual material structure. So this is something which works pretty well, and I brought again 2 videos here with me how this then could look like. Obviously here you have additionally some leading edges, and this is then combined with a SPH model of the, I go back once, if that works, with an SPH model to represent the gelatine, the soft body. So this was the first example. Secondly, we briefly step over into the automotive world. However, it implies a lot of the problems we are discussing here. We're looking at a crash absorber, so modeling and, let's say, or simulating and testing, and the whole world of crash absorbers is largely studied. If you look at the literature, there are tons of papers dealing with phenomena, with energy absorption characteristics, on how such crash absorbers should look like. And there are also a lot of modeling approaches which deal with modeling these crash absorbers. However, from our perspective, we couldn't find a modeling approach which actually is really in the position to do predictive modeling. What is usually done, you have experiments, and then you calibrate your model in order to represent your failure, your energy absorption characteristic to be used in a larger model. However, if you want to do such thing in a designing process, you need to be able to vary certain geometry aspects, especially the trigger angle, maybe the layer setup, and so on, diameters and stuff like this. So you don't want to have tests prior, but you want to do predictive modeling to actually be able to design your process parameters and your design space. So what do we see when we look at the experiments? We see, in this case, a rather complicated behavior. So it's not a typical, let's say, brittle behavior you see from CFRP material. It's a combination of course, the typical failure mechanisms here, like delaminations, but also you have a plasticity-like behavior coming from obviously the thermoplastic material matrix here. So you need to capture of course, the energy absorption structures, the energy absorption characteristics. That is the aim, but you definitely need to capture the phenomena happening within the trigger area, because this is governing the whole structural behavior. And of course, you need to somehow capture your failure behavior, your progressive failure, progressive damage behavior, or progressive failure behavior, delamination behavior during the impact process. So what have we done? We have firstly looked in quite a detail of what's really happening here, identified the relevant behavior, phenomena. What do we see? We see some intralaminar shear failure, especially here in the trigger area. So the trigger area is the area on the top of, or in the location, in the impact, in the crash location of the crash absorbing structures, and it depends on the angle, on the design of this trigger, on how actually the structural failure is then progressing. That's why it's called trigger, because it triggers different failure modes in the way depending on how it's designed. So what do we need to capture? We need to capture the phenomena in the trigger area. We need to capture this formation of a so-called debris wedge, which drives the failure. We need to capture the splaying failure mode, and also the progressive and stable crack growth, crack formation for the whole specimen, mainly or not mainly, also for delamination and fiber or shear failure. So we've chosen a multi-layer approach. Again, we went for high resolution into thickness direction. We have chosen to model each layer by three elements in thickness direction, connected with cohesive layers, which then may represent the failure, the delamination. So we ended up here in 33 single plies, of course, then connected with 31 cohesive layers. This is the quarter model. And what I'm not talking about, of course, we have done some material tests before of the material. We do know how the material actually behaves. And here it comes. Yeah, I forgot to point out that this was, still is a cooperation with a Korean partner, the Kims, who do some research on this, who we supported and collaborated on the modeling side, because they come from the material side. The material they have been chosen here came from an industrial partner, Korean industrial partner, and we tried to look whether it's suitable for crash absorbers or not. So, and here we come to actually a computing, not problem, but task. We realized that it's very beneficial to do proper decomposition, especially in this loading case where we have a very, let's say, a very localized phenomena. So it starts from the beginning in the impact contact area, so everything's happening there, so nothing is happening in the first couple of milliseconds in the lower part. So you want to have a nicely distributed decomposed net to have the computing power well used, and we learned that such a user-defined decomposition helps a lot to reduce the communication and the computational time in comparison to the, let's say, the more automatic or generic one. So this is something I wanted to point out, that this helped a lot to get the simulation running well. And we did the simulation then resulting with 144 CPUs in this case. And another, maybe a little cheat code, I would call it, is here that, of course, when we use our HPC capabilities to university, there's a queue where you need to wait how to use it, or when to use your the cluster. And here we worked with restart files actually to cut our computational effort into little chunks to get further up the queue, to be not to have put one big chunk in there which blocks the whole system. The system doesn't like that and re-queues us lower on, so we cut it in little chunks to be able to compute more quickly. This works quite nicely. Yes, what we see here a little phenomena that, of course, besides we cut it in equal steps, then let's say termination steps, the computational time, of course, rises since the element distortion and the lower time steps, which are then required. As a result, we end up with quite nice result, and I want to point out all the results I'm showing are really predictive results. Of course, we have performed tests, but we have done calculations before we actually did the test. We will see also some comparison between experiment and modeling. So this is very important to point out. The focus was on predictive modeling, and we have achieved this. So there are two main, let's say, patterns. If you look at the result, you can evaluate. The one is the global behavior. So how is the global behavior of this crash absorber is doing? So you might know that there are different phenomena might be happening. It might be kinking. It might go off. It might not do anything at all. So you want to make sure that structurally you have a nicely even crash front, which is going from up to down. from up to down, from the top to the bottom. If you look then at the, let's say, global energy, that's thanks for the reminder. And if you look at the force displacement curves, we are really proud that, and again I say this, it's predictive modeling results. We are really proud that these results correlate quite well with the experimental results we have been observing. And the second thing is you can really look at the details within this trigger area. You really are able now to evaluate what's actually going on there, which phenomena are triggering which failure behavior, and doing what successive failure, let's say, phenomena on the structural level. And our colleagues here did also a little visualization of the things we have done. So as a result, we could really say that we are very confident with our results and also with our predictive modeling capabilities here. And we will drive these further on, especially because we see that these discrimination behavior can be captured quite nicely, and this, as I said, correlates very well with the actual first force displacement curves we captured in the experiments. Okay, so and with a very little time left, I need to rush through the last piece of my presentation. So the last one is the high-fidelity modeling of, let's say, engine components with respect to FSE computing. There have been a couple of projects already dealing with that. We started with this 10 years ago in a project called High-Fidelity Virtual Engine. This I want to mention, of course, is all closely related to our cooperation to Rolls-Royce, who drove this these efforts and also provided know-how and capability with this. So we started with looking at the meshing process, the hex meshing process, which is a big a big challenge to do all hex meshes in such complex structural components. This was where we were working on. We developed workflows, how to decompose, how to simplify the models, how to do the meshing. We established the so-called methodology we call contact meshing, where we just stick together in areas which are not as important for the failure or for structural simulations, also only for stiffness. We just glued components together, which brought us into the position to make the meshing process much more efficient. This brought us then to a second project called Project Perfect, also of course with Rolls-Royce, driven by Rolls-Royce, where we then looked at automizing such meshing and simulation, or let's say model preparation processes. And this brings me to the actual example I want to bring here, the last stage of this, let's say, triology of projects, the project called Prestige, and this was closely carried out with our colleagues from the Institute of Fluid Dynamics, also at the TU Dresden, where the focus was set on actually take a large model, mesh it, bring it up for structural simulation, and then make sure that we bring it into the CFD analysis, apply the loads, and bring it back to do some structural analysis. So, and this all with very complex models. So quite a challenge, quite a task. Many partners were involved also besides of these. And I want to bring out the examples, some examples what we have been doing here. So the first step was, of course, 100 million elements. Okay, so what do we do now with this? We run implicit calculations to actually get the conditions on the working point in terms of temperature and in terms of rotative loads within these structures. So I have to say we paid some, some Lehrgeld. But we managed to do it, and in the end it worked fine. So we were able to do the meshing, transferring on the HPC, dealing with initial penetrations, look at the decomposition strategy, do the split runs to suit it to the HPC availabilities, and actually run the implicit calculations in terms of temperature and spin up, we call it, so structural results on in total 768 cores. And now we end up with the exact condition of these engine at the operation point in terms of rotational loads and temperature fields. And a second aspect then is, okay, now we have this very nice capability of really coping with these large models and how to deal with, how to run the calculations. Now we actually can really look at the details. What does small deviations in terms of the blades are actually doing? Okay, and of course, another buzzword, the digital twin aspect came in here. So what we did, and especially our colleagues from the ISM, they scan whole rotors, where each individual blade is scanned individually, and this geometry is then transferred into the mesh, or into the CAD model, and then transferred into the mesh. And this, of course, implies some challenges, because you need then be able to actually capture these deviations between the ideal CAD file and the measured CAD file. So you need to decide which micron is not relevant and which is relevant. So we developed a so-called, we call it mesh morphing process. This also involves some secondary software, and to really then sweep or transform the meshes we have initially created onto the geometry we then have resulting from the, let's say in this case, 3D GOM measurements. And the last thing then you can do, then you have the setup of the whole model. You have a very detailed real-time mesh, and then you can really run different scenarios. In this case, we applied a generic impact load case for FOD events, so for an object damage based on ice impact. And what we want to do, we run impact experiments, then map the deformations, with the resulting deformations, run down the model, run it up on a different working point, extract the resulting deformations, transform them, relate them into the CFD, where the CFD then predicts thrust and resulting efficiency, and then based on the pressure points, and then this can be again mapped back into the model to do further structure analysis. So this is the overall idea, and this is then how such a workflow looks like for one iteration, for one step. We do, again wrong, we do the pre-processing as I've shown. We do the FE analysis, spinning up, doing the impact experiments, and spin down, and then give it to the CFD analysis. In total, we have done this 50 times, and then each impact scenario has then been evaluated again with some kind of DOE 50 times in terms of the CFD modeling. One tool, the last thing I want to mention, one tool helped a lot. Maybe it's worth also for the community here. We stumbled across a so-called Python library, a lasso library, which which we were able really to handle this large data and extract the information out of, in an optimized way, out of our huge results files. And the very last slide I have here is then the final step, what we did, that we, as I said, we transform the structural analysis results into CFD modeling, and we were then able to, or together with the colleagues from Rolls-Royce, we were able to assess the effect of, for example, the diameter and the density of the hail balls with respect to the change of thrust, the efficiency, and the relative change in total pressure ratios. And all these studies can then be performed, and these are really results which have never been performed in this detail, and this is really my ending sequence, because you need exactly this very high level of resolution to be able to do such predictions. Because if you end up with a lower resolution net, you won't be able to detect differences in thrust or efficiency. So high fidelity modeling really enables a new field or a new space of information we can get out of these simulations. And with that, I thank you for your attention and close my talk, and I'm happy to take questions. Thank you.
Are there questions in the audience to the speaker? Are there online ones? So maybe I have one, because I have a former colleague working on these crash tubes. So really, yeah. And we were discussing that for a long time, so 7 or 8 years ago, and I was with my, let's say, high school mechanics. I tried to answer him these questions. He was on the production side. And what material model you use for these crash tubes currently? Yeah, sorry.
Yes, so obviously you have a whole load. LS-DYNA provides a variety of material modeling approaches. So in this case, we used a little different approach, because so in radial direction, so we used material 54, but not in a way you would think we would use it. We used the 1 and 2 direction in tangential and length direction, so that because we are focusing on the through thickness shear and failure behavior. And with this, we were able to model into thickness direction the, let's say, intralaminar shear failure and tensor and compression failure. And the intralaminar behavior was done by cohesive. I think it was 33, I think. 138. Exactly. 138. So we did it a little bit different. So it's not typically that where you go, how you do it typically, where you go for the circumference direction, we went into thickness direction.
Okay. Thank you very much. So I think I need to look back into my reinforced plastics lessons from university. Okay, so with that, thank you, Mr. Hornig, for your interesting speech.